Good day everyone, this is Engineer Aljan Michael G. Sabak and I welcome you to 6th discussion about Earth science. This time we will discuss more of the igneous and metamorphic rocks, how is it being formed and the processes behind it. Just sit back and relax while you are listening to the discussion. In the discussion of the rock cycle, we pointed out that igneous rocks form as magma or lava cools and crystallizes. Magma is most often generated by melting of rocks in Earth's mantle, although some magma originates from the melting of crustal rock. Once formed, a magma body buoyantly rises toward the surface because it is less dense than the surrounding rocks. Magmas can vary widely in composition, but in general they are made up of only 8 elements, in order of importance: oxygen, silicon, aluminum, iron, calcium, sodium, magnesium, and potassium. Viscosity increases with increasing silicon oxide concentration in the magma. Viscosity decreases with increasing temperature of the magma. The composition of magma depends on the rock it was formed from, by melting, and the conditions of that melting. Magmas derived from the mantle have higher levels of iron, magnesium, and calcium, but they are still likely to be dominated by oxygen and silicon. All magmas have varying proportions of elements such as hydrogen, carbon, and sulfur, which are converted into gases like water vapor, carbon dioxide, and hydrogen sulfide as the magma cools. The picture above are the magma types according to its chemical composition. Here we can see the trend that viscosity increases with increasing silicon oxide concentration in the magma and decreases with increasing temperature of the magma. Rhyolitic magmas usually have higher dissolved gas contents than basaltic magmas. Igneous rocks are composed mainly of silicate minerals. Chemical analysis shows that silicon and oxygen, usually expressed as the silicon oxide, content of a magma, are by far the most abundant constituents of igneous rocks. As magma cools and solidifies, these elements combine to form 2 major groups of silicate minerals. The dark silicates are rich in iron and/or magnesium and are comparatively low in silica. These igneous rocks can be classified according to its solidification occurrence. Those igneous rocks that are formed from cooling magma at depth are called intrusive igneous rocks or plutonic rocks. While those igneous rocks that form from volcanic activity, at or near the surface, or from lave from volcanic eruptions or activity are called extrusive igneous rocks or volcanic rocks. These igneous are also differentiated through its texture and it has an accompanying factor that can turn into different textured igneous rocks. One is we have the cooling rate. It means that the faster the cooling process the lesser the finer the igneous rocks. Second is we have the diffusion rate, meaning that the formation of chemical species is faster at higher temperature, and in lower viscosity meaning the more fine-grained texture of the igneous rock will occur or form. Lastly we have the 2, nucleation rate and growth rate. At larger degrees of undercooling, the nucleation rate will be high and the growth rate also high. This will then result in many crystals all growing rapidly, but because there are so many crystals, they will run into each other before they have time to grow and the resulting texture will be a fine-grained texture. To describe the size, shape, and arrangement of the mineral grains that make up a rock, geologists use the word texture. Texture is an important property because it allows geologists to make inferences about a rock's origin, based on careful observations of crystal size and other characteristics. Rapid cooling produces small crystals, whereas very slow cooling produces much larger crystals. As you might expect, the rate of cooling is slow in magma chambers that lie deep within the crust, whereas a thin layer of lava extruded upon Earth's surface may chill to form solid rock in a matter of hours. Small molten blobs ejected from a volcano during a violent eruption can solidify in midair. From the samples on your screen we can see that the left side is more on the fine-grained texture and it resembles a volcanic rock, meaning the cooling rate of the formation process is faster, thus it forms smaller or finer grained because it doesn't have time to grow. The right side of this image are the more coarser ones, since we can see visible crystals that resembles plutonic rocks, and it means that the process of formation of these rocks are much more slower compared to the volcanic rocks, thus it formed visible crystals that the latter. These are some of the examples of different igneous rocks with different textures. Here we can see that granite and rhyolite has the same chem composition but different texture. Same with andesite and diorite in gabbro and basalt. Another term for fine-grained igneous rocks are what we call aphanitic, and coarse-grained igneous rocks are also called phaneritic. Also, with increasing silica content, the rocks will become much felsic or lighter colored, and if it is decreasing it will become darker and it will turn into a mafic igneous rock. We have another type of texture, and this is what we call porphyritic. This is formed through two stages of crystallization, wherein magma partly cooled below the surface of the earth, providing time for the large crystals to grow, or phenocrysts, before it is extruded to the surface, forming the fine-grained matrix. The last texture type is the vesicular texture. These type of igneous rocks has voids that were created by rapid cooling, which causes air bubbles to be trapped inside. Olivine, pyroxene, amphibole, and biotite mica are the common dark silicate minerals of Earth's crust. By contrast, the light silicates contain greater amounts of potassium, sodium, and calcium and are richer in silica than dark silicates. Light silicate minerals include quartz, muscovite mica, and the most abundant mineral group, the feldspars. Feldspars make up at least 40% of most igneous rocks. Thus, in addition to feldspar, igneous rocks contain some combination of the other light and/or dark silicates listed earlier. Igneous rocks are also classified according to its color. These changes in color is caused by the rock's silica content and other minerals. These are the following designation of the color index of igneous rocks. These are the other trends with respect to the igneous rocks topic. As a summary, here we have different examples of igneous rocks based on different classification. Also, here is the summary of the trends that we have discussed all throughout. And on the next slides are some of the examples of selected igneous rocks. Andesite. This is a fine-grained, intermediate, extrusive igneous rock composed mainly of plagioclase with other minerals such as hornblende, pyroxene and biotite. Pegmatite. This is a light-colored, extremely coarse-grained intrusive igneous rock. Most pegmatites are composed of quartz, feldspar and mica. Basalt. This is a fine-grained, dark-colored extrusive igneous rock composed mainly of plagioclase and pyroxene. So we have done discussing igneous rocks. Now we will go deeper into the metamorphic rocks. Basically, metamorphic rocks comes from the word meta, meaning change, and from the word morph, which means form. Combing the two, these rocks have to changed in form to be a metamorphic rock. Rocks that form when a pre-existing rock, protolith, changes due to temperature or pressure, and/or as a result of squashing or shearing are called metamorphic rocks. Metamorphism is the change that takes place within a body of rock as a result of it being subjected to conditions that are different from those in which it formed. In most cases, but not all, since this involves the rock being deeply buried beneath other rocks, where it is subjected to higher temperatures and pressures than those under which it formed. On the other hand, metamorphism is the mineralogical and/or textural adjustments that take place in a rock in response to a new set of physiochemical conditions different from the ones under which the rock originally formed. Metamorphic rocks typically have different mineral assemblages and different textures from their parent rocks, but they may have the same overall chemical composition. With metamorphism, these rocks will underchange with the following different factors thereof. Temperature. The temperature that the rock is subjected to is a key variable in controlling the type of metamorphism that takes place. As we learned in the context of igneous rocks, mineral stability is a function of temperature, pressure, and the presence of fluids, especially water. All minerals are stable over a specific range of temperatures. For example, quartz is stable from environmental temperatures, whatever the weather can throw at it, all the way up to about 1800 degrees Celsius. If the pressure is higher, that upper limit will be even higher. If there is water present, it will be lower. On the other hand, most clay minerals are only stable up to about 150 degrees or 200 degrees Celsius. Above that, they transform into micas. Most feldspars are stable up to between 1000 degrees Celsius and 1200 degrees Celsius. Most other common minerals have upper limits between 150 degrees Celsius and 1000 degrees Celsius. Meaning, the increased heat allows chemical bonds to break easier. Pressure. Pressure is important in metamorphic processes for two main reasons. First, it has implications for mineral stability. Second, it has implications for the texture of metamorphic rocks. Rocks that are subjected to very high confining pressures are typically denser than others because the mineral grains are squeezed together and also because they may contain minerals that have greater density because the atoms are more closely packed. High pressures cause minerals with open lattices to collapse, forming more dense crystals. When forces are not equal in all directions, which is differential stress, minerals may deform and change shape. Time. Most metamorphic reactions take place at very slow rates. For example, the growth of new minerals within a rock during metamorphism has been estimated to be about 1 mm per million years. While the rate of metamorphism is slow, the tectonic processes that lead to metamorphism are also very slow, so in most cases, the chance for metamorphic reactions to be completed is high. For example, one important metamorphic setting is many kilometers deep within the roots of mountain ranges. A mountain range takes tens of millions of years to form, and tens of millions of years more to be eroded to the extent that we can see the rocks that were metamorphosed deep beneath it. Parent rock. The parent rock is the rock that exists before metamorphism starts. Sedimentary or igneous rocks can be considered the parent rocks for metamorphic rocks. Although an existing metamorphic rock can be further metamorphosed or re-metamorphosed, metamorphic rock doesn't normally qualify as a parent rock. For example, if a mudstone is metamorphosed to slate and then buried deeper where it is metamorphosed to schist, the parent rock of the schist is mudstone, not slate. The critical feature of the parent rock is its mineral composition because it is the stability of minerals that counts when metamorphism takes place. In other words, when a rock is subjected to increased temperatures, certain minerals may become unstable and start to recrystallize into new minerals. Fluids. Water is the main fluid present within rocks of the crust. The presence of water is important for two main reasons. First, water facilitates the transfer of ions between minerals and within minerals, and therefore increases the rates at which metamorphic reactions take place. It does not change the outcome of a metamorphic process, it speeds the process up so metamorphism might take place over a shorter time period, or metamorphic processes that might not otherwise have had time to be completed are completed. Secondly, water, especially hot water, can have elevated concentrations of dissolved elements, ions, and therefore it is an important medium for moving certain elements around within the crust. So not only does water facilitate metamorphic reactions on a grain-to-grain basis, it also allows for the transportation of elements from one place to another. These are solutions that chemically react with minerals. There are two types of metamorphosis. Contact metamorphism. This occurs adjacent to igneous intrusions and results from high temperatures associated with the igneous intrusion. And regional metamorphism. This occurs due to changes in pressure and temperature over a large region of the crust. This is a visualization of the two types of metamorphism. Other types of metamorphism are as follows. Cataclystic occurs as a result of mechanical deformation. like when two bodies of rock slide past one another along a fault zone. Hydrothermal. These are rocks that are altered at high temperatures and moderate pressures by hydrothermal fluids or hydrothermally metamorphosed. Burial. This is when sedimentary rocks are buried to depths of several hundred meters. Temperatures greater than 300 degrees Celsius may develop in the absence of differential stress. Impact metamorphism. This is when an extraterrestrial body, such as a meteorite or comet, impacts with the Earth or IIF. There is a very large volcanic explosion. Ultra-high pressures can be generated in the impacted rock. We can also identify metamorphic rocks through the following. Metamorphic textures. Grains are interlocked and grow in place. Metamorphic minerals. Certain minerals only grow under metamorphic temperatures and pressures. Foliation. Alignment of platy minerals or alternating layers of light, felsic, and dark, mafic, minerals. Now this is the process on how metamorphic rocks will form. First is recrystallization. This changes the shape and size of grains, but the same mineral remains. For example, sandstone may recrystallize into quartzite, then metamorphic reaction will occur. This is the result of chemical processes that decompose minerals and produce new minerals. After which it will undergo pressure solution, meaning the mineral grains dissolve where their surfaces are in contact, and lastly it will undergo plastic deformation. This is when minerals at high temperature can behave like soft plastic and become squished or stretched. There are two main types of metamorphic rocks. Those that are foliated because they have formed in an environment with either directed pressure or shear stress, and those that are non-foliated because they have formed in an environment without directed pressure or relatively near the surface with very little pressure at all. Some types of metamorphic rocks, such as quartzite and marble, which can form whether there is directed pressure or not, do not typically exhibit foliation because their minerals, quartz and calcite respectively, do not tend to show alignment. When a rock is squeezed under directed pressure during metamorphism, it is likely to be deformed, and this can result in a textural change such that the minerals appear elongated in the direction perpendicular to the main stress. This contributes to the formation of foliation. During shearing and compression, minerals become stretched, plastic deformation, all while recrystallization and neocrystallization is taking place. Think of this analogy. Think of stirring chocolate fudge into ice cream. The fudge starts out in a blob but gets deformed and smeared during stirring. These are some examples of a foliated metamorphic rock. And here we have the non-foliated ones. On this image, we can see the progression of metamorphic rocks from a sedimentary rock that is called shale. More heat and pressure will be needed in order to turn it into the next rock progression. Shale will become slate. Slate will become phyllite. Phyllite will then become schist. And schist with high-grade metamorphism will eventually become gneiss. Here is a summary scheme of the discussion. Please do familiarize these things as these are very important informations on understanding the processes behind metamorphic rocks. I hope you have a good time and you have learned something from this session discussion. See you on the next topic. Goodbye.